Alright, so collision note sheet that I posted up for you guys. Kind of looks like this. If you look in the week 2 folder, you'll see it. Basically, for these scenarios, I'm giving you an initial velocity, final velocities, and then also masses. And once we look at that, what we can do is we can take a look at the total momentum before, the total momentum after. We've kind of covered this in our lessons here, but that seems like a long time ago at this point here. So let's kind of go through it again, or at least put it on video so that everybody has some ability to bring all that stuff back that we did. So let me color code this as well. If I have a red one, I've got a blue one here. Made them both 0.75 kilograms, right? 0.75 kilograms, 0.75 kilograms. You got your objects coming in here with velocities here. 2 meters per second, negative 3 meters per second. Direction matters here, always does in momentum. They collide, they rebound. So here's your after scenario here. One object moving one way, another object moving another way. Negative 3 meters per second. And this one is 2 meters per second. Now, this one is classified as perfectly elastic. I don't believe we really got through every little aspect of collisions, but we'll get through it now. If you look at the total momentum of the two objects when you group them together, total momentum, sum them up. So you got 0.75 times 2, and you got 0.75 times negative 3. So what is that? It's negative 0.75 is the total momentum here. This is before. So after they collide, they each have new momentums. After, your total momentum is going to be 0.75 times negative 3 plus 0.75 times 2. And just looking at that, I can see I'm going to get the same answer. What you expect is that momentum is going to be conserved in these type of scenarios here. Anytime two objects collide, the combined momentum is conserved. So they each undergo changes in momentum, but when you sum up their momentums, should be no different. Now, that being said, you can also look at the kinetic energy. The kinetic energy initially, we'll do the totals here, it'd be 1/2 mv squared, right? So 1/2 times 0.75 times 2 squared. What's 1/2 times 0.75 times negative 3 squared? Keep in mind, when you square that, that's going to become positive. Your kinetic energy values are always positive. So summing up those two things, and what we have here is 4.875 joules. We'll do the final kinetic energy, the total. And this one should be pretty straightforward because, again, when you look at the numbers here, they're kind of set up so that it all makes sense. So just looking at them, I can see that these things are going to add up to the same thing as that. So we also have 4.875 joules. And what we have here is that for a perfectly elastic collision, both momentum and kinetic energy are conserved. That's very important because that's what defines what happens in this particular collision. If we go to the next one I've classified as inelastic. Simply inelastic, not perfectly inelastic, just inelastic. If you look at the numbers, I mean, the collision looks very similar, but, oh, wrong mouse. The numbers are a little bit different here. So let's take a look at the numbers. I actually gave them the same initial velocities here. Same masses as well. So we still have our initial conditions and then we'll have our final conditions. They come in towards each other, 2 meters per second, 3 to the left. They rebound here though, negative 2 meters per second. Now we're dealing with something different here. Then you got 1 meter per second here. Looking at the momentum before, we can sum it up. So the mass is still 0.75, 2 plus 0.75 times 3. And we saw that that was, excuse me, negative 3, sorry. That was negative 0.75. But now after, we have different numbers to deal with here. You got 0.75 times negative 2 plus 0.75 times 1. And what you're going to get here, again, is negative 0.75. So it still works out, right? It still works out that your momentum is the same. In fact, you're going to find that there's probably an infinite amount of combinations where momentum can be conserved with these initial conditions of 2 and 3 going at each other. But let's look at the kinetic energy numbers here, because this is going to be different here. The total kinetic energy here is going to be 1/2 times 0.75 times 2, square it, 1/2 times 0.75 times negative 3, square that. And again, what we should get is 4.875 joules. Now let's look at it after. Not going to be the same this time. We're actually going to lose kinetic energy here. And let's see why. You got 1/2, 0.75. And then this is moving at negative 2 square, but that'll end up becoming all positive when we do that. 1/2, 0.75, positive 1 squared. So we got to add those up. And we don't get the same amount of energy as we had before. What I'm getting here is I'm getting 1.875 joules. So what we have here is basically a loss of 3 joules. Basically what ends up happening is, if you guys remember me banging those steel balls together on the piece of paper and watching them burn up, that energy doesn't just get dissipated out into thin air. What it actually does is it heats both objects up ever so slightly. And what you saw is that, that heat can sometimes be enough to burn some paper, even with, very small objects. So that's what's happening here. And this one's classified as simply inelastic. Now, what we have here is that, again, momentum is conserved. Momentum will always be conserved in collisions, but we have kinetic energy here is lost. So that's the difference between perfectly elastic and inelastic. Now we got a special case that we're going to deal with here, and that's the one that you see with the train cars here. Perfectly inelastic. Basically, if you take a look here, you got one train car coming in, one at rest. They're going to lock, they're going to move, and what they end up moving with is a slower velocity in the end here. So here we go, 2,000 kilograms. Coming in, 10 meters per second. 2,000 kilograms. Not moving at all. Alright, so that thing has all the momentum. You look at the momentum, the initial momentum, we'll be able to do it. They collide, and what they're doing is they're both moving at 5 meters per second. They're in unison. What happens is that they stick. That's what makes this perfectly inelastic. That's what it means to be perfectly inelastic. Your objects are forced to stick together. We did not see that happening in the previous collision here. So if we look at the momentum before, pretty easy, 2,000 times 10 plus 2,000 times 0. What do we get? 20,000. A lot more momentum because it's a train. All right. After, momentum after. What we end up having here is that they're both moving at the exact same speed. So you got 2,000 times 5 plus 2,000 times 5. Do the math here. you're going to get 20,000 again. Momentum is conserved. Momentum is always conserved. Kinetic energy, what we're going to find is we're going to lose a lot of kinetic energy here. The initial kinetic energy would be 1/2 times 2,000 times 10 squared. The other one we don't have to do because it's not even moving. So what do we get here? 100,000 joules. It's a lot of joules. Final kinetic energy. Now, you have the option of doing them both individually, or you could group them together. It's entirely up to you. You're still going to get the same thing. So we could do 1/2 times 2,000 times 5 squared. Plus 1/2 times 2,000 times 5 squared. Or you could do 1/2 times 4,000 times 5 squared. It's going to get you the exact same answer. So what do we have here? 50,000 joules. Lost 50,000 joules essentially. So we started out with 100,000 joules, we lost 50,000 joules. What you're going to find is that momentum is conserved. Kinetic energy is lost. A lot of people go, hey, what the heck is the difference between this and what you just did? It's just the fact that they stick. That's what classifies this as perfectly inelastic. Alright, we're 11 minutes in. Let's do the recoil in a separate video.